Hello, and welcome to Lecture 14 on the topic of simple AC circuits. Here we're talking about alternating current. Up to this point, we have only talked about DC current, direct current, like the type of current that comes from batteries. But now we're talking about a whole different type of power supply. This represents a fundamental side of physics and one that we're really just going to touch on in this lecture and in Lecture 15. This is firmly planted in the realm of electromagnetism because the very generation of AC current and AC voltage is through an electromagnetic effect following Faraday's laws and Lenz's laws. Look back at those lectures to review those ideas. We're absolutely building on many ideas here, considering that this is the 14th lecture in electricity and magnetism of a 16 lecture sequence. So we are very near the end, very much at the pinnacle of many ideas. Okay, let's take a look at our objectives. We want to learn the basics of an AC circuit with a single resistor and the meaning of the root mean square, current and voltage. We want to learn the basics of an AC circuit with a single capacitor and the resulting phase shift between current and voltage across the capacitor and the meaning of something called capacitive reactance. Okay, we want to learn the basics of an AC circuit with a single inductor, the resulting phase shift in that case, and the voltage and the meaning of an inductive reactance. So same idea, but for inductors as for capacitors. We also want to learn about transformers. We want to learn how they function and how to calculate changes in current and the result from changes in voltage. Okay, that result from changes in voltage. Let's get to our key terms. Our first key term, no surprise, is alternating current itself, AC. Okay, and this definitely is in contrast to DC. You got AC and you got DC. So AC is the type of current found in outlets and from generators. Okay, now obviously both types of current are very common, DC from many batteries, but this is AC current. Okay, also very common. It is naturally created from the uniform circular motion of a coil in a uniform magnetic field. Okay, so think about the idea of changing magnetic flux, as I said a moment ago, Faraday's law and Lenz's law. That's how AC current is naturally generated. Okay, and so it makes so much sense whether it's a natural source of energy like a wind turbine, or a dam, a water dam, or it's a turbine that's spinning from the burning of a fossil fuel. All those cases, you got rotation of a coil in a constant magnetic field, constant and uniform magnetic field. Okay, so very fundamental type of energy formation. All right, electrical energy formation. AC is sinusoidal. Okay, so it's going to be described as a sine function, which should be no surprise considering I said that it's naturally created from uniform circular motion. And uniform circular motion and basically oscillations and oscillation functions as sine functions are intimately connected mathematically and physically. Okay, here's a picture of what it would look like. A sine function of current is a function of time, right? There's our current function of time. The period of this oscillating current would be just the reciprocal of the frequency, or 2 pi over the angular frequency, because angular frequency omega is 2 pi times frequency. Okay? All right. Now, interesting thing about the term AC current, and it always kind of bugs me, the term is misleading since outlets and generators are actually a fixed voltage source, not a fixed current source. The current is dependent on how much resistance is in the circuit that you attach to that outlet. So it really isn't AC current, it's AC EMF or AC voltage, but for whatever reason, the term stuck and we always call it AC current. Okay? All right, so let's define what the root mean square is. You may have seen this before in discussion of thermodynamics, but it's a mathematical expression, and it is the square root of the mean of the squares of a value. Okay, I know it's a mouthful, but this is what it looks like, right? So consider three numbers, 2, 4, and 5. All right, actually it should be 3, 4, and 5. And I decided to change it, but didn't fix it there, so I'll change it over to a 3. That should be a 3. Okay, so you can see here correctly expressed as 3, 4, and 5. All right, so you sum up the squares. So we sum the square of 3, the square of 4, and the square of 5. Then we take the average of the squares, and then we take the square root of that average. Okay, and so the value then in this case would be 4.08. So the interesting thing about the RMS of a set of numbers is that it's always larger than the mean. Because in this case, and that's why I changed it to 3, 4, 5, we can clearly see without any calculation that the mean has to be the middle number. It's 4, all right? And obviously 4.08 is a little bit bigger than the mean. Now, obviously for continuous values, it's a little bit different, but you can imagine, at least numerically or computationally, splitting this sine curve into many, many individual values, and you're doing the same mathematical process, okay? That's what we mean by the root mean square. The voltage and current for AC circuits are often expressed as RMS values, which is a mathematical convenience, kind of the scope of which is beyond the class, but we'll just use it because it is very common with regards to using Ohm's law, okay, and similar relationships, okay? All right, so moving on to reactance. I mentioned this in the objectives. This is a new term, and I know we already have so many terms like capacitance and inductance and all these, all these different ideas. But reactance is fundamental, and it will be rather a nice change because it will allow us to use Ohm's law when talking about capacitors and inductors, which we've never done before, okay? So it is the quantity given to capacitors and inductors that represents the circuit element's ability to impede, which is to slow down the current, okay? Now, it doesn't make sense to talk about reactance for capacitors and inductors for DC circuits, okay? Reactance works in a similar way to resistance and has the same units. And that's why I said it's kind of nice to work with reactance because we'll always talk about it's always ohms, okay? Now, technically, the reactance of a resistor is its resistance, so we just call it the resistance. But the point is that it's always measured in ohms, so pretty straightforward there. But as I said, it only applies to AC circuits, okay? That's why we've never mentioned it before, because in a DC circuit, as we know, you charge a capacitor and it's done. But in a current or a voltage source that's going up and down, the capacitor is constantly being charged and discharged. So then it actually affects the current over time because a capacitor that takes a long time to charge and discharge is going to have a greater effect on the current than a capacitor that quickly charges and discharges. That's the idea of relative impedance, which is expressed as reactance, relative reactance showing up in Ohm's law, measured in ohms. Okay. Right, and obviously we'll show the equation that allows us to take the units of, say, a capacitance over to ohms, all right, or inductance over to ohms. Now, finally, the transformer, okay? Transformers are part and parcel of the power grid. We see them on power lines all over the place. We see large transfer stations, and the idea of a transformer is it changes voltage. It physically is a set of side-by-side coils, so like a solenoid, right, that are used to change voltage. Here's a picture of a transformer, okay? There's always a primary coil, which is the input, and a secondary coil, which is the output, okay? And I call these 1 and 2. These are the subscripts that show up in the equations. So the primary coil has N1 turns. The secondary coil has N2 turns. If you want the transformer to do something, N1 does not equal N2. That's the whole point, okay? A step-up transformer increases voltage. A step-down transformer decreases voltage. Both are used. Voltage is stepped up from a power plant to very high voltage over long-distance power lines, and then stepped down incrementally to the voltage of 120 volts in your home, okay? Ideal transformers have no energy change, so if the voltage increases, then the current must decrease, and vice versa. Okay, because you don't get something for free. If you increase the voltage, you got to give up current. That's actually a desirable effect, though. So that's actually the reason we step up the voltage. Okay, and transformers in practice have an iron core, which helps direct the magnetic field. Okay, all right. Let's take a look at this important diagram. Right, a lot to unpack here. The idea is we've got a couple of three cases of a AC voltage source. So notice the schematic. Notice that this is a circuit element that's represented a little bit differently than a battery, right? Which we're used to looking something like this. Okay, so a AC voltage source is usually shown as a sine wave within a circle. Okay, it is a voltage source, and we've got a resistor, we've got a circuit with a capacitor, and then we got one with an inductor. So we're keeping it really simple here. We'll combine some ideas in lecture 15, our final lecture on circuits. But here we just want to consider these circuits individually. A circuit with a single AC circuit and a single resistor, single AC source and capacitor, and then lastly, inductor. Okay, down below, however, are these interesting graphs because they show that there is a phase angle or a synchronicity or a lack of synchronicity between the signals in these different types of circuits. So let's start with the one that is by far the simplest. If we just have an AC source and we run it through a resistor, well, obviously the bigger resistor means less current. So you're going to have, so the current is affected by the resistor. Here we're assuming that the value of the resistor is something larger than 1, so our actual magnitude of current is less than our voltage. But the point is that they're in phase, right? Because we're essentially sloshing electrons back and forth, right? At one point they're being pushed in this direction, a moment later they're being pushed in this direction. And as they do that, they're being pushed through the resistor, changing some of that electromagnetic energy into heat energy, okay? So, but everything is in phase. Okay, well, the capacitor certainly isn't the case. Now, that shouldn't be a surprise because we've seen RC circuits before. We've seen that RC circuits have a time-dependent behavior. Charging up the capacitor, capacitors charge quickly at first and then more slowly over time, okay? Think about how they build up charge over time, okay? Asymptotically approaching with an exponential function a final value of maximum charge. Because of that effect, there is a phase angle between the voltage and the current, okay? So now we see that the voltage is shifted from the current, okay? In other words, when the current is maximum, the voltage is 0. When the current is 0, the voltage is maximum, okay? Now the inductor, same idea here, right? When the current is maximum, the voltage is 0. When the current is 0, the voltage is maximum. The difference, though, is the direction of the shift, okay? So, in summary, for resistors, the current is in phase with the voltage. However, for the capacitor, the voltage is pi over 2, or a quarter of a period out of phase, and it's shifted behind the current, okay? So we see that the voltage lags the current. That makes sense because the capacitor takes time to charge up. Okay, so capacitors create a lag, all right, a quarter period lag. And a quarter period is represented as pi over 2 because a full period is 2 pi in terms of the radian periodic nature of this sine function, okay? All right, lastly, we've got the inductor. Now we know the inductor is the opposite. Inductors don't take time to charge. Inductors immediately respond to change, and they if there's a large change in current, then they'll prevent that current from flowing, okay? So inductors actually have a phase shift ahead of the current. So for the inductors, the voltage is pi over 2, or a quarter period phase shifted ahead of the current. Okay, and again, review the last lecture in lecture 13, where I introduced the inductor and the idea of why it behaves that particular way of completely stopping the current initially, and of course it comes down to the idea of Lenz's law and creating an opposing EMF. Okay, all right. So these are the fundamental principles that are so important to this lecture and understanding how resistors, capacitors, and inductors work in AC circuits. Furthermore, notice that under each of the graphs, there is a time-dependent function, all right? So these functions actually allow us to express the instantaneous value of voltage for a circuit with an inductor and an AC circuit, or AC source. Likewise for a capacitor, right? So this is instantaneous voltage, instantaneous current, okay? So notice the functions represent the phase shifts, okay? Negative sign, phase shift to the head, sign, phase shift to behind, or expressed within the cosine as a phase angle, okay? Either positive or negative. All right, so I bring these up because we will actually use these equations. I want you to consider these equations part of the key equations, okay? All right, and now moving on to the rest of our key equations, let's take a look at how IRMS and VRMS, which is root mean square, are expressed, okay? Well, they are just the maximum value, which is the amplitude of the sine function, or the shifted sine function, divided by the square root of 2. Okay, that's how it works out for continuous values rather than a set of discrete values like the example I gave of 3, 4, 5. All right, so it ends up being that IRMS is about 70% of the amplitude of the current. Likewise, the root mean square of the voltage is about 70% of the amplitude of the voltage. Okay, all right, now moving on to expressing power with these values of root mean square current and root mean square voltage. Well, the average power, right, measured in watts, is just the same power law, I squared R or V squared over R. It could also be I times R, right? But it's always going to be VRMS, okay? Or at least that's one way of expressing it, a new choice. Okay, we can also express Ohm's law in terms of these root mean square values. Excellent, okay? It's just good to know these all work. Okay, and now something fundamentally new, reactance. Okay, so X sub C is capacitive reactance, again, measured in ohms, and it's equal to 1 over 2 pi times the frequency times the capacitance of the capacitor. Or we could replace the 2 pi f with the angular frequency omega, okay? So capacitance measured in farads, all right? And then f is the frequency, okay? And the angular frequency omega equals 2 pi r, and there we have the frequency. Frequency is measured in hertz, right? Hertz, by the way, are just inverse seconds. So what's interesting about this formula is it tells us that capacitive reactance actually goes down as capacitance goes up. So as you have a bigger and bigger capacitor with more and more farads, then you're actually going to have less and less reactance. It's going to impede the current less and less. So a really big capacitor doesn't have a big effect on the actual current. All right, if you think about Ohm's law, right, how this is going to work, because down here, notice that I wrote Ohm's law again, but with capacitive reactance replacing R. See? All right. So then the idea, right, if you have a very large capacitor, then you're going to have a small capacitive reactance, which means then you're going to get a lot of current for a certain amount of voltage. Okay. All right. So Ohm's law for AC capacitor circuits. Okay. Now, naturally, the next one is inductive reactance, okay? Also measured in ohms. It's represented as X with a subscript of L, and it's equal to 2 pi F times L, right? So very similar expression, or omega L, all right? The only difference is it now, our value of the circuit element isn't in the denominator, it's in the numerator, okay? So we see then that if inductance, measured in henries, goes up, then reactance goes up. So the bigger the inductor, the bigger the reactance, which means according to Ohm's law, the smaller the current for a certain voltage. Okay, so they definitely play different roles. Okay, at least in terms of how they affect the current directly in individual circuits like this. And finally, we've got the transformer equation, just relating the voltage in the secondary coil, the voltage in the primary coil, and the number of turns in each coil. All right, so output voltage is V2, number of turns in the secondary coil is N2, number of turns in the primary coil is N1, and then naturally the input voltage is V1. Okay. And note, since ideal transformers conserve energy, the power in the primary coil is equal to the power in the secondary coil for an ideal transformer, which we'll talk about. We'll also talk about one that's slightly not ideal, in which case you just tack on a percentage or basically a value in front, okay? And since that's the case, we can express the power as V1 I1 equals V2 I2. So that tells us that the output current must look like this, all right? Just kind of naturally follows from the transformer equation above. Okay, well, let's get to our practice problems, our examples. Okay, so we got 4 types. So type 1, problems that involve AC circuits with resistors and making calculators with root mean square values of voltage and resistance and average power. Okay, then we're going to get into AC circuits with capacitors, AC circuits with inductors, and lastly, transformers. Okay, all right, so just natural way to split up the problems. Let's take a look at example 1. An AC voltage source with a peak output of 122 volts is connected to a 54 ohm resistor. What is the RMS current through the resistor? Okay, well, if we know the maximum value, we know that RMS is just the maximum value divided by root 2. So we just take the 122 and divide by root 2, and that gives us 86.3 volts. Okay, excellent. All right, so then the IRMS, so that's the voltage, but I asked for the current. So then we're going to use Ohm's law to find the RMS value of the current, okay? And I take the value that I found above for the RMS value of the voltage, divide it by the resistance of our circuit, and there we go, 1.6 amps, okay? Now that's not the maximum current, right? If we wanted to find the maximum current, we'd simply take the 122 volts and divide by the 54 ohms, okay? But we were asked for the RMS current, so there it is. Okay, and we want to find the average rate of energy dissipation, okay? So that's this formula here, power average. And there's obviously different versions of it, but I'm just gonna use this one since we already know both these values, simply a matter of multiplying them together. But obviously we could use the square of the RMS voltage over R, or the square of the RMS current times R, all right? And so 86.3 volts times 1.6 amps, again, these values up above, and that gives us 138 watts as our average power. Okay, not our maximum power, right? And not our minimum power, because the minimum power is going to be 0 because all these signals are sinusoidal, they pass through 0. There's a point where there's no power, right? But this is the average power. Okay. All right, example 2 has some more steps to it. Example 1 is very simple, obviously. The voltage source of a generator is given by this function. Okay, so this is the first time we're actually seeing the actual functional form of the instantaneous value of voltage. Okay, this is the sine function. Okay, excellent. The generator is connected across a 215 ohm resistor. By inspection, what are the maximum voltage, the frequency, and then find the RMS voltage across the resistor and RMS current and so on. So let's start with the inspecting it and finding the maximum voltage. So I say inspection because we just want to look at this function and recognize what we're looking at here. Now this function should look similar to functions for waves and harmonic oscillators. They're expressed in a very similar way, right? Except then it would probably be displacement or velocity or acceleration. That would be your time-dependent function. But here it's voltage, okay? So Vmax is the amplitude of the function. The amplitude of the function is that term right there, okay? It is the 2.34 times 10 to the 5 volts, okay? And then the angular frequency is what's inside, right? Because this is sine of omega t. So we know then that omega, the angular frequency, is 140 pi measured in radians per second. So then if we want to find the frequency, we simply divide by 2 pi. So that tells us that our frequency is 70 hertz. Okay, very good. All right, now we're going to do some calculations and find the RMS voltage across the resistor. Well, that's just a matter, as in the example above, of dividing by root 2 from the amplitude, which is the maximum voltage. And we get 1.65 times 10 to the 5 volts. And then let's go ahead and find the RMS current. I bet you can guess we're going to use Ohm's law. Sure enough. All right, so plug in our values, and we get 770 amps, right? So very high current. Okay, and then in part E, we want to find the maximum current in the resistor. Well, if we know the RMS current, it's simply a matter of multiplying by root 2, right? So we can then just take that 770 and multiply by root 2 rather than divide by it. So we find that the maximum current is 1090. Again, the minimum current is 0, right? Because again, it passes through 0, right? And there's going to be a point where the current is negative 1090 because it's flowing the opposite way, right? But the maximum magnitude is 1090, okay? Now let's go ahead and find the average power as asked in part F, okay? Well, that's simply a matter of using the power equation. We'll go ahead and use this one since we just solved for IRMS up in part D. All right, plug in our values, and there we go. We have an average power output of 1.27 times 10 to the 8 watts, a lot of power, okay? Now something pretty novel here, part G, what is the instantaneous current at this particular time, right? And this time is 5 milliseconds. Okay, so we use the function to find the instantaneous voltage and Ohm's law for current. Okay, so we're gonna actually use the function of instantaneous voltage. Okay, so we plug in our 5 milliseconds into the function, okay? And note that this time is about a third of the period, okay? Now, did I ask for the period? No, but we look up here on the hertz is 70 hertz. So then the period is about 1 over 70, all right? And that would be in seconds, okay? So this value is about a third of that, okay? And it gives us a value of about 1.89 times 10 to the 5 volts, okay? All right, so not the maximum voltage certainly, but nowhere near 0 either, okay? And then we're going to use that to find the instantaneous current at this moment at the 5 millisecond mark. And so simply plug in the instantaneous voltage that we found, divide by the resistance, which is not time dependent, and then we find out that we get 881 amps. What's interesting about this is this value is greater than the IRMS, but less than the maximum, all right? Which makes sense because it's a third of a period. And if you think about the current is going to start as a sine function, come up at a quarter period, be maximum, at a half period, be 0, all right? So this is 1/2 a period right there. Well, a third period is going to be somewhere in between. So it's somewhere between peak and 0, and it's a little bit above RMS, okay? All right, let's go on to capacitors. Example 3. When a 47 microfarad capacitor is attached to an AC source, its capacitive reactance is 42 ohms. If instead, two 150 microfarad capacitors are attached in parallel to the same source, what will be its capacitive reactance? Okay, so we want to find the AC frequency from the values. Okay, so we're just going to use the definition of capacitive reactance and solve for F. Okay, so here I've just rewritten it to solve for F. And we'll go ahead and plug in our values because we are given the capacitive reactance and we are given the capacitance. Okay, notice this raises to -1 power, just another way of writing 1 over. And we get 81 hertz as our frequency. Okay, all right, so now that we know that frequency, that's the frequency of our source, now we can consider what happens when we change the value of C, the value of capacitance. Okay, so now we're going to find our new capacitive reactance for our new setup of capacitors. Okay, so C prime is a new capacitor. All right, so here it is with our new value capacitance. Notice I have 300, and that's because it is 2 capacitors in parallel, which is simply 1 plus the other, right, or just 2 times each, okay? All right, if they're in series, I'd have to use a different expression, but here they're in parallel. All right, so then we end up with 6.6 ohms. Indeed, the capacitive reactance went down as the capacitance went up. Exactly what we'd expect from this expression here and the mathematical relationship I mentioned a few minutes ago. Okay, all right, moving on to example 4. When a 6 millifarad capacitor is connected to a generator whose RMS output is 56 volts, the RMS current in the circuit is observed to be 0.3 amps. What is the frequency of the source? Okay, so a lot of these problems you can see is all about piecing together information and then using the appropriate equations. Okay, there's a rather small pool of appropriate equations, so we should be able to sort it out. Okay, so here I'm going to use Ohm's law with the expression for capacitive reactance. Okay, and I know that then I can isolate capacitive reactance like this from Ohm's law. Okay, and I know that capacitive reactance is also equal to this by definition. Okay, all right, so then I can then use this right here, this equivalency, to solve for f. All I've done is take these two expressions, set them equal to each other, and solve for f, because I know everything. I know IRMS, I know VRMS, right? Okay, so there I plug in my RMS value for current, I plug in my RMS value for voltage, 2 pi, and I plug in my capacitance. All right, so there we go. We find out that the frequency is 0.14 hertz. Very, very slow. Why so slow? Well, because we're actually getting a lot of capacitive reactance here. I never went back and actually solved for the value of capacitive reactance because it wasn't asked for. But if we want, now that we know F, we could plug it back in and actually find the value of capacitive reactance. But I can tell it's a big number because we have a lot of volts, 56 volts, but we're getting a rather small current. So that's requiring a lot of capacitive reactance. Well, 6 millifarads is not a very big capacitor. So how can you get so much capacitive reactance, so many ohms of impeding the current with a relatively small capacitor? Well, the other way to do that is just run the circuit really slowly. And that's indeed what we have to do. We have to have a very low frequency, less than 1 hertz, right? So it takes more than 1 second for the circuit to go through a full cycle, a full oscillation. Okay? All right, now on to inductors. Okay, so in the inductor of a 59 hertz AC series circuit, the peak voltage precedes the peak current in each cycle by what time interval? So how do we go about this? Well, the phase shift we know is 1/4 of a period ahead. The period is 1 over the frequency. So the time interval is, well, just 1 over 4 times the frequency. Okay? So it'd be, in this case, because we're given a particular frequency, it'd be 1 over 4 times 59 hertz, or 4.2 milliseconds. Okay? So that's the actual amount of time that the voltage precedes the peak current. Okay? All right, very good. Example 6, all right? So in an AC series circuit, the inductive reactance is 41 ohms, and the frequency is 137 hertz. What is the inductance in the circuit? Okay, if the max voltage across the inductor is given as this, then what is the instantaneous current through the inductor 2 milliseconds following when it's negative Vmax? Okay, so there's going to be a bit more to do with part B, but I think we can definitely tackle part A. And again, you should think that part A is very similar to what we were just doing for capacitors, but now we're doing it for, of course, inductors. Okay, so here we're going to use our definition of inductive reactance. Okay, so the bigger the inductor, the bigger the inductive reactance. Okay, the more it impedes the current. And here we're just going to solve for the actual value of inductance, L. All right, and so we know the inductive reactance, we know the frequency, so it's simply a matter of plugging those in, and we end up getting 47.6 millihenries. Okay, or 47.6 times 10 to the negative 3 henries. Very good. All right, what about part B? Okay. All right, so here, for inductors, we know that the voltage is equal to the negative of the amplitude after 1/4 of a period. Okay, so 1/4 of a period. And refer back to the graphs to see like when that happens, okay? So 1/4 of a period after time equals 0 is the first time that V equals negative Vmax, okay? Essentially, you know, we're dealing with this. This is our function, okay? And that's our time right there. Here's our axis t. This is our point. This is our 1/4 of a period, see? Okay? All right, and by the way, this is voltage. Okay, so very good. Now we know we want to take that 1/4 of a period and add an extra 2 milliseconds, okay? Because that's going to be our t that then we're actually going to plug into our expression for instantaneous voltage, okay? So we're going to have 1/4 of a period, okay? We know that our period is just the reciprocal of the frequency, so 1/4 of that is this value right here, all right? And then plus 2 milliseconds, and that gives us 3.83 milliseconds. Very good, all right? Okay, and this is very close to half a period. So that's interesting because that's taking us very close to the point where it's going to be zero, right? Okay, so then we're going to find the current at that moment. Okay, so then we go back to our expression for current. Okay, current is expressed as cosine because it's a different phase, right? You know, we have sine for, see, we have negative sign for the voltage across the capacitor, but we've got cosine for the current, like so. Okay, very good. All right, and so but now we have our value of t, so we're just going to plug that in. All right, we already know the frequency, and we know the maximum voltage. All right, because we know it's 10, and we now know our inductive reactance. Notice that what I've done here using Ohm's law, I've just replaced I max. Okay. Okay, which I think I have a note for. All right, yeah, I have it here. Because 10 volts over 41 ohms is none other than the current amplitude, which is 0.244 amps. Okay, all right. So we're getting to a point, right? I said, you know, this is close to half a period, so that's going to correspond to almost no voltage across the inductor. Well, almost no voltage across the inductor should correspond to almost maximum current. Okay, because whenever the current is almost maximum, that means that the inductor has basically no voltage across it. Okay, whereas when the current is changing from zero, when the current experiences the greatest change, then that's when the inductor has a lot of voltage across it, because that's the way inductors work. They oppose change, and more rapid change, bigger opposition, bigger voltage, bigger induced EMF. Okay, but here we have almost no induced EMF, thus we have a very large current. And another way to think about maximum current is maximum current corresponds to the peak. Well, the tangent line, the slope at the peak, is essentially flat, so the rate of change is very small. Again, inductors care about rate of change. Okay, all right, example 7 is more with inductors. Here I decided to ask about a couple of other things that you can ask for, magnetic flux and energy stored in inductors for these oscillating circuits, okay? I did leave off the value here. I meant to specify the number of turns in the inductor because we will need that for part A. Okay, so a 45 millihenry inductor with 120 turns is connected to a source of sinusoidal EMF with an angular frequency. Instead of giving you the frequency, I give you the angular frequency of 63.7 radians per second and a maximum EMF of 20 volts. What is the maximum magnetic flux through the inductor? Okay, so this is our expression for inductance as related to number of turns in the inductor, in the solenoid, magnetic flux, and instantaneous current. Okay, all right, and we also know that from Ohm's law, current is related to the voltage and the inductive reactance, like so, and we know we can replace the inductive reactance with just omega L. Okay, very good. Okay, so then we can go ahead and rewrite this expression, okay, which is, I introduced in our lecture on inductors and inductance, and is considered one of the definitions of inductance. And so we can replace it with solving for the magnetic flux just by rewriting it, okay? And notice here I have I max, right? So I'm just specifying that the current I care about isn't RMS or anything, it's the maximum current. And then I'm going to replace the maximum current with this expression from Ohm's law, right? And from the definition of inductive reactance. And notice that the actual value of inductance just cancels out, all right? And so then we have that the magnetic flux is just going to be equal to 20 volts over 63.7. Now this is the maximum, by the way. Okay, now there's different values of magnetic flux. At some points the magnetic flux of the inductor are 0 or anything in between, but this is the maximum case, so corresponding to the maximum voltage. Omega is a fixed value for the circuit, and there we go, 0.31 Webers, right, which is equivalent to Tesla area, okay? All right, so there's part A. Now in part B, at what time after t equals 0 does the instantaneous amount of potential energy stored in the magnetic field of the capacitor reach 1 joule for the first time? Okay, this is an interesting one. Oh, I did notice a mistake here, something I left off. I want to specify something for part A. It's so interesting. This number of turns is giving me a lot of trouble, because you can see here that I have the number of turns there, and then I ended up not solving for it, right? So when I replaced I just left off n. So n should be right here, and so I should have 120 in my denominator. I'll go ahead and fix that, because that's going to significantly change the amount of magnetic flux, because this is magnetic flux in each turn. And so if there's 120 of them, you have to spread that magnetic flux out per turn. And so it's just going to be this value divided by 120 to give you the magnetic flux per turn, okay? All right, so then I just need to add the n. I'll correct that in the notes after the fact. Okay, so now finally on to part B. Okay, so here, since we're talking about stored energy in the inductor, we're going to use this expression for the stored energy in an inductor, 1/2 Li squared. All right, and so here we're going to replace I with the time-dependent expression for I. Okay, because what we're going to do here is we're actually going to solve for t. Okay. All right, so that's what I'm going to start doing here. I'm just going to start isolating t. One of the first things I do is, multiply both sides by 2, divide by L, take the square root of both sides to get rid of that, okay? Then I'm going to do divide by I and do an inverse cosine, all right? And then the only thing within the cosine is the omega. That's why I'm leading 1 over omega. So we get this big old expression for the time, all right? So this is the time for a particular value of energy. Quite interesting, okay? Plug in all my numbers because I know everything. I know the angular frequency, I know the maximum voltage, I know the inductance and so on, right? And I would specify how much energy I wanted. And there we go, we got 4.7 milliseconds. Now it's hard to make sense of that number, so I want to explain it a little bit. All right, so this is small compared to the period, because it turns out that the period, based on our angular frequency, is 99 milliseconds. All right, but this is a tiny fraction of that. And that's because the inductor begins with full energy. And so therefore, and the value of the max amount of energy that this particular inductor, so if this was I max, then we would have maximum potential energy. Well, that's equal to 1.1 joules. Well, 1.1 joules is pretty close to 1 joule. So since the system starts with maximum energy in the inductor, we have a time that's pretty close to t equals 0, which is why it's so small compared to the period. Okay? All right, finally, 2 examples about, well, transformers. Okay, so example 8. An ideal transformer has 60 turns on its primary coil and 30 turns on its secondary coil. If 120 volts at 2 amps is applied to the primary, what voltage is present in the secondary, and what current is present in the secondary. So this is a very straightforward example. All right, so I'm just going to use the formula for transformers and go ahead and solve for the voltage, 600. Okay, so it just goes up based on the ratio of the number of coils. Okay. And then to find the current, just go ahead and use the fact that the power is equal to each other, and then find the current, and it goes down by the ratio of the voltages, which is the same as the ratio of the coils, and it ends up being 0.8 amps. Right? So voltage went up, current went down. Okay, now one that's a little bit more involved. Suppose 2 megawatts is to arrive at a large shopping mall over a single 0.1 ohm line, right? That's the resistance in the power line. Estimate how much power is saved if the voltage is stepped up from 120 to 1200 volts and then down again, rather than simply transmitting at 120. All right, and assume the transformers are each 98% efficient. Okay, all right. So we're going to start by finding out how much power is lost without the transformer. Okay, so this is just if we left it running at 120. Okay, so this is just P lost, which is going to be I squared times R. Okay. Now, I squared, we can rewrite as P over V. So we're just replacing it with, because we know the amount of power, right? We know we want to deliver 2 megawatts, okay? So we don't know I, so all I'm doing is just putting it. Now, we could solve for I, but instead I'm just going to do a substitution, okay? And so that ends up giving us a power loss of 2.78 times 10 to the 7 watts. I mean, that's incredible. That's almost 28 megawatts. So that means we're losing way more power than we're actually delivering, right? Talk about inefficient, okay? So I guess 120 volts isn't great for transmitting on lines that have so much resistance, right? Okay, well, let's see. So with the transformer, the voltage is increased and the current is decreased according to, well, this relationship, because this is not an ideal transformer. This is 98% efficiency. So that means the power in the secondary is only 98% of the power in the primary. All right, so then we can go ahead and rewrite both the powers as V times I, the product of V and voltage and current, and then go ahead and solve for the output current, right? And so our output current now, notice that the number of, basically the higher voltage, we weren't given the number of turns, but the higher voltage shows up as 1200 volts. So that's gonna cause a decrease in current down to 1700 amps. And again, we didn't solve for the initial current, right? But it's a lot more than 1700. I think it was in the hundreds of thousands, all right? Maybe about a million amps. So here we have a much reduced current, okay? Now it would be reduced even more if it wasn't for the slight inefficiency. Okay, so with this reduction in current, the power loss is also reduced, because notice that the power loss is proportional to the current. So less current means less power loss in the line. Okay, so now we're going to have power lost prime, the new one, using the new current, the current that is the output current from the transformer. Okay, so plug in our 1700 amps. All right, same resistance, that hasn't changed. And now we have a power loss of only 280, basically 290,000 watts. So now our power loss is still huge, but at least it's less than the actual power we're delivering, okay? And then if we want to find out how much we saved, we're just going to take the difference in the power loss, all right? How much was lost without the transformer, how much was lost with the transformer, and we see that there's a huge savings of 27.4 megawatts. Really a remarkable savings, because we literally went from losing over 10 times the energy that we're delivering to losing about a tenth of the energy we're delivering. So orders of magnitude change. Okay, all right. So there we have our last transformer example and our last example of simple AC circuits. I hope this lecture has been lots of fun and has been very informative. Thank you so much for watching.